Hello everyone. Myself Dr. Bibin Christopher, Assistant Professor, Department of Computing Technologies from SRM Institute of Science and Technology, Kottangloto. So in this video lecture, I'm going to handle a session named as Error Detection and Error Correction. So which will come under your computer communication course. So in this lecture, what I are going to discuss is, so we just want to know what is this error detection as well as error correction. So we already heard like this error detection and correction plays an important role while transferring data in your computer communication, right? So whenever we are transferring a data or whenever we are moving a data from a sender to the receiver, so definitely there will be some error in the data during the transmission, right? So those errors has to be detected and the same has to be corrected. Then only the recipient will receive the original data which the sender is being transmitted. Okay. So here we'll try to find out how the error how we'll try to find out so what type of errors we are having and how we can overcome or how we can correct those errors if they occur. Okay, so with that we'll have a basic we'll just categorize the errors which is being occurred in our computer networks as two types. One is called as single bit error and another one is called as burst error. Okay, so what is this single bit error? So from the name we can trace out like so when there is an only one bit of change in the given data, that is either so if you are changing it from either 1 to 0 or the bit is changed from 0 to 1, only one bit of data is being changed, we can call that it as a single bit error. Okay. And what about this burst error? So burst error in the sense if two or more bits of data or two or more bits of data unit have changed either from 1 to 0 or 0 to 1, we are calling it as a burst error. So these are the mostly occurred error in our data communication or computer communication, right? So and here we are quoting the example so of your single bit error as well as your burst error. So let us check the first diagram. So the first diagram we are representing it as a single bit error. Why? Because the colored 0 bit is being changed to 1. Okay, so there is only one bit of data changed, so we are calling it as a single bit error. Then there comes an right hand side figure which is representing your burst error. So there two or more bits of data has been changed. Okay, so two or more bit of data in the sense, see for example, so here first the 0 is changed to 1 and 1 is changed to 0. Again in the upcoming bits 1 is again changed to 0 and 0 is again changed to 1. So there we are having almost some 4 bits have changed either 1 to 0 or from 0 to 1. Okay, so more than two bits of data has been changed, so we are calling this as your burst error. Okay, so how to find out or how to find out or how to detect those type of errors? So there we are having some error detection mechanisms or error detection methods which is being used to find out or which is being used to identify the type of errors, right? So here we are having some two different main methods of finding out your error. One is called as your cyclic redundancy check. I will be normally calling it as your CRC, and another one is called as your checksum. So these two methods plays an important role in identifying or to finding out an error in your computer communication, right? So there comes a concept called as a redundancy. In order to find out an error or in order to identify an error in your data, what we need to do is we need to add an additional or extra bit to the original data, right? So the addition of an original data into the normal data, we are calling it as an redundancy. Why this redundancy bit, or we are calling it as a redundancy bit? Why this redundancy bit is being added in the data? So to find out whether the data which is being transferred from the sender to the receiver is having an error or not. Okay. So this redundant bit or this redundancy bit is being removed by the receiver when the original data with the redundancy bit has been received. Okay, that is the original role, or that is the main role which is being played by your redundancy bit. Okay, so this redundancy plays an important role into or to identify identify whether there is an error being occurred in the data or not. Okay, so how to create an redundancy bit is, so this is an example over here. So we are having a data bit as 1010000 something, and with from that data what we are doing is we are using a generating function. This generating function will generate an redundancy check bits. Okay, so this redundancy check bits, we are calling it as a redundancy data. So this redundant data is being added to the original data. So as we already explained, like, so the redundancy bit or the redundancy data is used only to identify the errors, right? So we'll be adding or we'll be summing up the data with the redundant bit, and it is being transferred to the receiver. So the receiver receives the data and the redundant bit, and he will pass that particular received data to a checking function. So that checking function will check whether there is an error or not. Okay, so if there is any error, it will reject the particular data. If there is no error identified, it will accept the data. So how to identify an error? So if there is any change in the data which is being transferred from the sender to the receiver, okay, we can call that it is an we can say that there is some changes occurred in the data, and if there is some changes, now automatically the redundant bit will also get changed. So the redundant bits, if there is any change in the redundant bit, it will reject the original data, or else it will accept the data. Okay, so there are certain different error detection methods. Okay, so these are the different error detection methods which plays an important role in your data communication. So one is called as your VRC, second one is called as your LRC, third is called as your CRC, fourth one is your checksum. So in the first previous slides we might have discussed that CRC and checksum plays an important role there. So why? Because the most widely used and the most efficient methods of identifying an errors is nothing but your CRC as well as a checksum. So we are mainly focusing on that, and we just want to know the other schemes also called as vertical redundancy check as well as logical redundancy check. So we'll have an overview of these two, and we'll try to quote some drawbacks what is being faced in your VRC as well as LRC, and we'll move to the CRC as well as checksum redundancy check in your data communication, right? So the very first method which we are going to check is called, which we are going to have is called as the redundancy check. So sorry, vertical redundancy check. Okay, so this vertical redundancy check is also known as your parity check. So what is this a parity check? So the parity check is nothing but it is again an redundant bit which is added to the original data in order to make the original data to be of even parity or odd parity. So we need to know what is this even as well as what is this odd parity, right? So even parity in the sense, when you try to count the number of ones in our data, if it comes in an odd number, if it comes as an odd number, we are calling that it is an odd parity. So then what about this even parity? When you are trying to count the number of ones in the original data, if the original data or if the number of ones in the data seems to be of even, we are calling it as an even parity. Okay, so this vertical redundancy check, otherwise called as parity check, and even though we are having two parity checking methods, we'll be mainly focusing on even parity, and we try to find out the number of ones, or we'll try to make the number of ones in our original data added with the parity bit to be of even. Okay, so here comes an example how to make an data to be of even parity. Okay, so the data which we are getting from the user is 11000001. Okay, so there we will be having an even parity generator. So this even parity generator will try to find out how many number of ones are there in the original data. So when you try to count out the number of ones in the data, so we'll be having 111. So totally we are having 3 ones there. So 3 ones in the sense it is of odd parity, right? So we are always focusing on a even parity when we are trying to have it as a vertical redundancy check bit. So in order to make this data bit to be of even, what will be, or what we are going to have is, we just want to add an extra parity bit called as 1. Okay, if you add this 1 here, if and after that when you try to count out the number of ones in the data, what we'll be getting is, we'll be getting 4 number of ones which is of even parity. Okay, so we just make the data to be of even parity, and we'll transmit this particular data to the receiver. So the receiver, what he will try to do is, he will try to retrieve the data, and he will again check for the parity. Okay, so after checking the parity, and again if the parity is again an even parity, then the receiver will accept that there is no data modified and it's the original data. So like that he will accept the data. Okay, so here is another example how we'll process our vertical redundancy check. And the example is nothing but, if the source wants to transmit data unit 1100111 using an even parity to the destination. Okay, so there we are having a data bit as this one, and this even parity generator will generate, or will count the number of ones in the data. So the number of ones in the data is 11111. So altogether we are having 5 number of ones there. So in order to make the data to be of even parity, we need to have, or we need to add one more extra one. So that parity 1 bit will get added there. So we just made this data to be of even parity right now. Okay, so this even parity data bit is being transferred to the receiver, and the receiver, after receiving the data, again he will try to check the parity, and while checking the parity, if it is of even parity, again he will try to accept the data, or else if it is of odd parity, he will try to reject the data. Why? Because the parity has been changed, and he assured that there is some data surely modified. Okay, so he will reject the data if there is any change in the parity. Okay, so there comes some advantages as well as disadvantages. So the advantages in the sense, so this VRC can able to detect a single bit error. So we all know, like so we are going to have only an even and odd parity, and it will try to find out only a single bit errors. And even though we are saying it will try to find out a single bit error, it will identify, or it will detect burst errors also. But there comes a situation, or there comes a rule, like when the number of bits changed is in the order of 1 3 and 5, 1 3 5 and 7, so odd numbers have changed, no? We will try to identify, or it will try to find out the error. Okay, say for example, it is very efficient to find out a single bit error. Okay, so if one is changed to 0, or 0 is changed to 1, it will try to easily identify. Okay, if and in addition to that, if two number of bits, or if one bit as well as 3 bits, or 5 bits, or 7 bits has been changed, now it will try to identify it. Okay, so what will happen if two number of bits has been changed? So two number of bits has been changed is, say for example, there we are having 1 and 0 in your data. Okay, if we are having, if you are trying to change this as 1 and 1 to 0 and 0 to 1, automatically the parity won't get changed, right? So if you are having an even number of parity bits changed, it won't find out the error. Okay, so that seems to be a drawback or disadvantage of your vertical redundancy check. Okay, so there comes a second one called as longitudinal redundancy check. This longitudinal redundancy check, we are calling it as your two-dimensional parity check. Okay, so this will make your data into rows and columns. So the block of data will be divided or will be put in an matrix format as rows and columns, and will be added all the redundant bits. Also will be adding all the data bits, and will find a redundant bit there. So that redundant bit with all the data bits has been transferred to the receiver. So the receiver will collect all the data plus the redundant data, and he will try to find out the he'll try to find out again the redundant data. If the redundant data which is being transferred from the sender as well as the receiver seems to be same, it shows like there is no alterations or there is no change in the data. Okay, if there is some changes in the redundant data which is being calculated in the receiver end, then the receiver will identify like there is some changes done in the original data. Okay, so here is an example for this. So if a block of 32 bits is to be transmitted, so it is divided into a matrix of 4 rows as well as 8 columns. Okay, so 32 bit of data we have to transfer. So that 32 bit of data has been divided like 1 2 3 4 4 rows with 8 bits each. Okay, so totally 8 into 4 is equal to 32 bits of data. So all these 32 bits of data has been added together, and this added data is called as a redundant data or LRC bit. Okay, longitudinal redundancy check bit. So this LRC bit is added again with the original data, and all together it is transmitted to the receiver. Okay, so at the receiver all the data has been received, and the receiver will try to find out the LRC, longitudinal redundant check bit at the receiver end. So if at the receiver end there is no changes, or the redundant bit both at the center as well as the receiver end calculated seems to be same, and it will try to identify that there is no change in the data. So here in this example we have quoted like there are 1 as well as 3, so total 4 bits has been changed, and so this 4 bits has the changed 4 bits has been identified as this one. So we have mentioned it as an underline over here. if there is some changes here, automatically the LRC which is being calculated now, definitely we'll be having a change in that. If there is some change, or there is a change in the data, automatically we can say like there is some data has been changed during the transmission, and the receiver won't accept the data. So that's about your LRC. So advantages in the sense, this LRC can be used to identify or to detect burst errors, and it is again, so the drawback of this is it is not able to detect error if 2 bits of data, if 2 bits in the data unit are damaged and 2 bits in the exact position or same position of the data is also damaged. Okay, so if the data bits changed is a 2 as well as it's again in the same position, it can't identify the error. Okay, so that seems to be a drawback. So in order to overcome these drawbacks, what we are having is we'll be going for the third method called as your cyclic redundancy check method. So which we are using a normal method for identifying or to detect your errors. Okay, so this is the most powerful redundancy check technique called as CRC. So this method uses a method called as a binary division. Okay, so unlike your LRC as well as VRC, so though those uses your binary addition, but here it will make use of a binary division to perform this CRC method. Okay, so the original data bit is being divided by an dividend bit, and the remainder what we are getting after the binary division we are calling that is your CRC bit or a CRC reminder. Okay, so this CRC reminder is being added with the original data which we have transferred now, which we want to transfer, right? So the original data with the CRC bit of data has been added together and it is being transmitted to the receiver. At the receiver end, what the receiver will do is he will again try to perform this binary division method. So in this binary division method, after doing this binary division, if the error or sorry, if the remainder is 0, the data is being accepted at the receiver end. If other than 0, if you are getting an 1 or 100 or 1000, if you are having a remainder like this, then the receiver won't accept the data, and the receiver is damn sure that there is some problem occurred in the data. So this is the overall principle, or this is the overall method how we were CRC, cyclic redundancy check bit, has been worked. Okay, so we are having an original data. The original data is being added with n number of 0 bits. Okay, so what is this n number of 0 bits? Why we are going for adding n number of 0 bits, and how we have calculated? We have a divisor bits, no? So if the divisor bits is 5, we have to add 4 number of bits to the original data. So n minus 1. So if the divisor is n plus 1, we need to add n bits of data with the n bits of 0, n bits of zeros to the original data, and we need to perform a binary division over there. We will be getting a remainder, and the remainder bit we are calling it as an CRC, so which is shaded as an yellow, no? So CRC bit. This CRC bit is again added with the original data, and this is being transferred to the receiver, right? So the receiver, after receiving the data plus a CRC bit, he will again perform a binary division method. With the binary division method, he will try to find out the remainder. If the remainder what he finds is at 0, he'll accept it, and other than 0, if you are trying to get an answer, so the receiver is trying to reject the original data. Okay, so the algorithm for your CRC is nothing but what we have explained from the diagram of the same concept. So we need to append zeros, we append n number of zeros if you are having a divisor as n plus 1, and we need to perform in a binary division with the modulo 2 binary division method, and the resultant remainder we are getting as an CRC. This CRC bit is being added with the original data, and the same has been transferred to the receiver. The receiver, after getting the CRC bit with the original data, he will try to find out the binary division again, and he will try to find out the remainder. If the remainder is 0, he will accept the data, or else the data is being rejected by the receiver. Okay. So this CRC can be generated as a polynomial. Okay, so in polynomial it is being represented as like this. So x power 7, x power 6, x power 4 plus x power 3 plus x plus 1. So if it is being given, we have to take it as, for the x power 7 it is taken as 1, x power 6 it is taken as 0. There we don't have any value for x power 5. So in the place of x power 5 we will be putting as a value as 0. And x power 4 again we are having 1, x power 3 we are having 1, and x power 2 there is no value, so we will be giving it as again as 0, and x power x we are having, so we will be giving an value as 1 and again plus 1. So like this, if we are having a CRC polynomial, it is being given, we have to take an value like this. Okay, so the standard CRC polynomials which is being given, or which is being used for your CRC is nothing but the CRC 12, CRC 16 bit, the CRC ITU, T, and NOR, and at the most we will be using the CRC 32 bits, so which you have learned, or which you might have seen in most of the places, right? So normally we will be using the CRC 32 bits of data. So these are the standard polynomials which is being used. If it is in CRC 8, we'll be using it to our ATM header. Okay, asynchronous transfer mode header, we'll be using it. If it is an CRC 10 bit, the mostly this ATM AAL layer will be using this, and the CRC 16 can be used by this HTLC and this data link layer LAN. No? So this LAN will be using your CRC 32 bits of data, right? So this is a simple polynomial representation So if you are having a polynomial as x power 6, 5, 4, 3, 2, 1, we'll be putting in values for that as 1, 1, 1. And if there is no polynomial, we'll be having it putting the value as 0. So this we know, right? So polynomial as well as a divisor. So polynomial is there and a divisor value. So instead of this x power 6, 4 and 3, we don't have any values there, no. So we'll be putting or we'll be marking this as 0. Okay. So here comes an example how we are calculating this CRC. So here is an example as suppose sender want to transmit the information string as this one. The receiver and the sender decide to use an arbitrary polynomial pattern, which is nothing but 1, 1, 0, 1, which is the divisor. Okay. So we learned like this CRC is mainly used mainly uses your binary division method. No, the original data with the original data we need to append some n number of zeros. The n can be calculated from the divisor polynomial. If the divisor polynomial is 4, so here we are having a divisor polynomial is 4, and what we are trying to do is we are trying to add 4 minus 1. So 3 number of zeros we have appended over here, and we are performing in binary division and we are getting a remainder as a triple one, so 111. So this we are calling it as your CRC bit, right? So this CRC bit 111 is being added here and it is being transferred to the receiver end, and again in the receiver we will be performing the same binary division, and in the binary division we are trying to find out the remainder, and the remainder is nothing but 0. So we are finalizing like there is no changes in the data which is being transmitted, right? So the data is being accepted by the receiver. Okay. So this is again the same example, so which we have seen there. So in a diagrammatic view, we have explained this. We have a data polynomial. We have a data with the number of zeros appended together, and we are performing this division of modular division of binary division method, and we are getting an remainder as 110, which is nothing but an CRC bit. So this CRC bit is being added over here, and we are trying to find out the remainder as a 0. So the data is being accepted over here. Okay. So if in case if there is some changes in the data, say for example here they have changed the code word, they have changed a single bit in the code word from 1 to 0. Okay. So if you are changing this data, definitely what you will be getting is we are getting a remainder as 0, 1, 1, and this remainder shows like there is some alterations done in the data and the receiver won't accept the data. Okay. So the last method of this identifying errors in your data communication is nothing but your checksum. So this checksum plays again an important role. So the error detection, so which is being used in your higher layer, is called as your checksum method. So this checksum method is again based on the concept of your redundancy. So we'll be using a redundant bit to find out the error. Okay. So at the center side, a checksum generator will be there, which divides the number of segments into n blocks. So normally it will be dividing it into 16 blocks at a maximum. Okay. So these segments are added together, and after adding we'll be getting a result. No, that result will be taken as in the result will be taking an ones complement, and that ones complement data is being added with the original data and it is being transferred to the receiver end, and then at the receiver end again they will be adding up and will be trying to calculate the redundant data. So if the redundant data is if the redundant data is 0, or if the redundant data is having all ones, we'll be trying to accept it, otherwise we are trying to reject the data. So here is an example how your checksum is being done. So the data is being divided into n number of bits, okay, and all the n number of bits are sections we are adding together, and the sum of this is being added. The sum of this is being added, and we are finding an complement of this, and this is your checksum. So this checksum bit is being again appended with the original data, which we have, and at the receiver end again the same sections be added with the checksum also. While adding all those things with your checksum, if you are getting an value as ones, we will be accepting the data, otherwise the data is being rejected. Okay. So the explanation what we have done from the diagrammatic representation is here. So the unit is divided into k section, which is of n bits. So all the data, so one's complement we have to take, and this one's complement is being added with the original data, and that same data is being transferred to the receiver. So at the receiver, what we'll be doing is again the same data with the checksum bit or checksum data will be added together, and we are trying to find out the resultant as 1. So if it is 1, we'll be accepting it, otherwise we'll try to reject that data, right? So the performance of this checksum is nothing but it will try to find out all type of errors involving odd number of bits. Okay, so it's a maximum. So if it will try to find out the burst errors. So there comes again on a problem there. If one or more bits of the segment are damaged, and the corresponding bit or the bit of opposite value in the second segment is also damaged, the sum of all those columns will not get changed. Say for example, if you are having a first segment as 0 0, okay, so instead of this 0 0, we are changing it as 1 and 1. Okay, like the same case in the second segment we are having a value as 1 1. So instead of this 1 1, if it is being changed as 0 0, there we don't get any changes in the sum which we are being calculated. Okay, so that is why that is the problem again in your checksum method. If two number of bits is being damaged in the first segment, and again same set of two bits again changed in the second segment also, there we don't have any changes in the checksum which is being created. Okay, so that seems to be again a problem in your checksum. Okay, so I think with this we have come up with all the error detection methods as LRC, longitudinal redundancy check, vertical redundancy check, your checksum, as well as your cycling redundancy check. So these different methods of error detection is being explained thoroughly, and you can go through this particular video to know more about your error detection methods. Okay, thank you.